And welcome back, students. As we continue our discussions about linked lists, today we're going to discuss big O, runtime, and efficiency. So getting started with today's lesson. If you were to ask a programmer how fast his or her program is, you might expect an answer like 2 seconds, 1 second, 12 seconds. It depends upon input. Well, the speed of a program, you can't really define it by a single number, like saying like 2 seconds, for example. Sure, you can find ways to count it, but there are some factors that kind of play into how fast your program is. So, for example, a program will typically take a longer amount of time on larger inputs than it will for smaller inputs. So if you input 1,000 things versus 10 things, obviously it's going to take a lot longer to put the 1,000 things in versus the 10. Now, you would expect that a program, for example, sorting numbers, would take a lot less time to sort 10 numbers than it would to sort 1,000. It makes sense. You only have 10 numbers to sort versus 1,000. If you were to do it on your own, and let's say you scale down, if you sort 3 numbers versus 10, it's going to take you not very long to do the sort of 3 versus the sort of 10. Now, it might take you only 2 seconds with your program to sort 10 numbers. But maybe for you to do that 1,000 numbers, your program takes 10 seconds. So that really leads us to the question of how fast is our program then? Well, the programmer really kind of has to set up a table of values for how long the program took for different size inputs. And you can see we have a table right here. So we have like 10 numbers is 2 seconds, 100 is 2.1, 1,000 is 10, 10,000 is 2.5 minutes. All right, now if you look at it, there's not a single time within this table. However, we do have different times for a variety of different input sizes. And now we're starting to get a little bit of a mathematical equation here, because we could set this up, we could plot these points and try to find a line of best fit. So this, of course, leads back to math. Remember, computer science is based around math. You can't escape it. So the table is the description, in this case, of what is called a function in mathematics. We have an input-output. Now, just as a non-void Java method takes an argument and returns value, so too does this function take an argument, which in this case is input size, and returns a number, which in this case is the time the program takes an input of that size. So if we call this function t, then t of 10 is 2 seconds, t of 100 is 2.1, t of 1,000, 10 seconds, and t of 10,000, 2.5 minutes. Well, that table is not obviously every single possibility there is. It's just a sample of some of the values of this function t. We could have a continuous function. It's not discrete. The program will take some amount of time on inputs of every size. So although they're not shown in the table, there's obviously also values for t of 1, t of 2, etc., 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 pretty much t of any size that the program can physically handle in memory can run through this application. So therefore, for any positive number n, t of n is simply just the amount of time it takes for the program to sort n numbers. The function t, therefore, is called the running time of the program. All right, with that out of the way, let's examine then what does it mean for us to have a worst case runtime. So far, we've only been really assuming that the sorting program will take in the same amount of time on any list of n numbers. Well, that's not always true. Perhaps it may take less time if the list is, like, for example, already sorted or almost sorted. So, for example, if you have a list of, let's say, 100 numbers that are already almost sorted, like let's just say there's just one number that needs to be moved, obviously, that's not going to take as long as a list of, let's say, 50 numbers that's completely unsorted. Because, well, there's only one number swap that really needs to occur, technically, with the almost sorted array. In this case, therefore, t of n is defined to be the time taken by the hardest list. That is, the time that's taken on the list of n numbers that makes the program run the longest. This is, of course, called a worst case running time. Now, in this chapter, we're always going to mean worst case running time when we give a running time for an algorithm or from some code. So we're looking at things from the worst case perspective. Not the best case, but from the worst case. So the time taken by a program or algorithm is often given by formulas, such as 4n plus 3, 5n plus 4, or even n squared. Now, if the running time of t of n, let's say, is 5n plus 5, then inputs of size n, the program run for 5n plus 5 time units. So that means, if you have, let's say, a t of 2, so it's saying you have 2 inputs, so the time equivalency should be 5 times 2 plus 5, so that would be 15. So let's take a look at this from a coding perspective since we're talking more programming. So this is some code to pretty much just search an array with n elements to determine whether a particular value is in the array. So I have int I equals 0, boolean found equals false, while I is less than n and not found. If a of I is equal to target, found is set to true, else plus plus. So we're just going to increment. So what we ultimately want to do here is compute some estimate of how long it's going to take the computer to execute this code. So with that searching algorithm, how long is it going to take to find that number? Well, we would like an estimate that does not depend on which computer you use, because obviously if you have a supercomputer or a quantum computer, or it's going to be a big difference between if you have like a little tablet. Now, there's other reasons because, well, for example, if I just write a program and I'm going to say, hey, I'm going to distribute this out to different people, well, we don't necessarily know which computer is going to be used, or we may even use several different computers to run programs at different times. Like I might use, for example, a school device now, or I might go home and run my own computer, which is more powerful. We don't necessarily know all the different scenarios. Now, one possibility, of course, when you're looking at this is to count the number of steps. But it's not necessarily easy to decide what step is. And we kind of actually did some of this back in programming 1. We looked at like a bubble sort versus selection sort. We did a counter that pretty much kept track of each iteration. So in this situation that we're looking at, the normal thing to do is to count the number of operations, which is kind of like what we did with the counter. It's like every time it would move through the sort, it would increment this counter that we could keep track of the number of counts that it would do. Well, in this case, our term operations, it's kind of vague, just like the term step. But there's some agreement in what the practice is about what qualifies as an actual operation. So, for example, let's just say that for our Java code that we have on the previous slide, each application of any of the following will count as an operation. So equals, less than, and, not, using brackets, equals, even plus plus. All right, obviously, you can throw other ones in there, for example, like minus for a decrementer as well. Now, the computer must do other things besides carrying out these operations. But these seem to be the main things that it is doing, so we're going to assume that they account for the bulk of the time needed to run this code. Because obviously you have like background processes and stuff like that going on too. In fact, our analysis of time is pretty much going to assume that everything else in the computer takes no time at all. So we're pretty much just going to ignore it. And that the total time of our program to run is equal to the time needed in order to perform these operations. Now, although this is an idealization that is clearly not completely true, so this is obviously not perfect of how we can truly analyze the runtime, it does turn out, though, that simplifying our assumption pretty much kind of works well in practice. So it's often made when you're either going to analyze a program or an algorithm. Now, even with simplifying our assumption, there are still two cases to consider. And that is either that the value target is in the array or was not in the array. So let's first consider the case when the target was not in the array. The number of operations performed will depend on the number of array elements searched. The operation equals is performed 2 times before the loop is executed. Now, because we are assuming that the target is not in the array, the loop will be executed n times, 1 for each element of the array. Now, each time the loop is executed, the following operation is performed. We have a comparison of less than, we have an and, we have not, and there's brackets, you have the double equals, and you have plus plus. All right, so if you count that all up, you have 5 operations for each of the n loop iterations. Because how many symbols do we have there? 5. So, finally, after n iterations, the Boolean expression is again checked and found to be false. Therefore, that's going to add final 3 operations, less than, and, or not. Now, if we tally up all these operations, we're going to get a total of 6n plus 5 operations when the target is not in the array. Now, we're going to leave this as an exercise for you to do in the later on, pretty much just to confirm that the target is in the array. Then, if it is, though, the number of operations is going to be 6n plus 5 or less. Therefore, we can really conclude that the worst runtime of this particular searching algorithm is T of n equals 6n plus 5 operations for any array of n elements and any value of target. So, look at that. We just determined that the worst case running time for a search code is 6n plus 5 operations. But an operation, though, is not a traditional unit of time. So if you come to someone and say, yeah, it's 6n plus 5 operations, they're going to be like, oh, what? But if you start saying things like nanoseconds, seconds, minutes, people are like, oh, yeah, I get that, because they understand that concept of time. So if we just want to know how long the algorithm is going to take on a single computer, well, we just know how long it takes that computer in order to perform one operation. If an operation can be performed in 1 nanosecond, for example, then the time will be 6n plus 5 nanoseconds. If an operation can be performed in 1 second, well, then it'll be 6n plus 5 seconds. If we use a slow computer that takes 10 seconds to perform an operation, the time will be 60n plus 50 seconds. Okay, and of course you notice that this is of course in 60n, because notice we're still in our base unit of seconds, but in order to count for that extra 0 here, we have to add a 0 to each of these numbers. All right. In general, if it takes the computer c nanoseconds to perform one operation, then the actual running time will be c times 6n plus 5 nanoseconds. Now, we did say approximately because we are making some simplifying assumptions, and therefore the result may not necessarily be the exact running time. This means that our running time of 6n plus 5 is ultimately a very crude estimate. So to get the running time expressed in nanoseconds, you must multiply by some constant that depends upon the computer you're using. Now, our estimate, therefore, of 6n plus 5 is only accurate due within a constant multiple. All right, so we've talked about all this worst case stuff now. What does that lead to? Well, our big old friend, big old notation. Now, we did discuss this a little bit back, I believe, in Programming 2. We talked a little bit about some of the big O stuff, like how you analyze different things. We might have even done a little bit in Programming 1. I think we talked a little bit about it as well when we talked about different sorting algorithms. But we have kind of looked at some of those stuff before. All right, big O, if you remember, what does it do? It looks at worst case runtimes. That's what its job is. So let's examine how that means in context, therefore, for our data structures. So estimates on running time, such as the one we just went through, are normally expressed within big O notation. Now, suppose we estimate the running time to, say, 6n plus 5 operations, and suppose we know that no matter what the exact running time of each different operation may turn out to be, there's always going to be some constant factor c, such that the real running time is either less than or equal to c times 6n plus 5. Understand, these circumstances, when we talk about this kind of stuff, we say that the code or program or algorithm or whatever we're talking about runs in time of big O 6n plus 5. So, of course, when we read that, you don't say, oh, 6n plus 5, it's big O, because there's also a little o. So keep that in mind, big O of 6n plus 5. All right, we don't necessarily need to know what our constant c will be. In fact, it's undoubtedly going to be different for different computers. But we must know that there's one such c for any reasonable computer system. So, for example, if the computer is very fast, so let's say it's like a supercomputer, well, c might be less than 1. So let's say 0.001. Now, if the computer is very slow, the c might be very large, say 1,000. Now, moreover, because changing the units, say, from, let's say, nanosecond to second involves only a constant multiple, there's necessarily not really a need to give any units of time. Now, remember, big O estimate is what's known as a upper bound estimate. That's why we kind of talk about with the worst case scenario. We always approximate by taking numbers on the high side rather than the low side of the true count. All right. So if you had a range, let's say, of values, when we talk about upper bound, if it was, let's say, a number between 40 and 60, we're going to err on the side of 60 because we want to look at that upper bound. Also notice that when you're performing a big O estimate, we need not determine an exact count of the number of operations being performed. We need only estimate that is correct up to a constant multiple. Now, if our estimate, let's say, is twice as large as the true number, no, that's fine. Yeah, because, again, we're looking at the upper bound. Now, an order of magnitude estimate, such as the previous 6n plus 5, contains a parameter for the size of the task involved by the algorithm or program or piece of code. In our sample case, this parameter n was the number of array elements to be searched. Now, not surprisingly, it takes longer to search a larger number of array elements than it does a smaller one. Now, big O running time estimates are always expressed as a function of the size of the problem. So, in our chapter, when we look at this kind of stuff, all our algorithms would typically involve ranges of values within some kind of container. So in all those cases, n is going to be, in that case, the number of elements within that range. Now, the following is kind of a more alternative or pragmatic way to think about how big O estimates work. So the easiest way to think about this is really from the big scope of things. You start getting big picture. You only really want to look at the term with the highest exponent. So whatever's got the biggest exponent, look at that one. And then really don't care about everything else. Just don't even pay attention to the other constant multiples. All right, these big O running time estimates are pretty crude, but they do contain some valuable information that is very important to look at. If you want to get down to specifics of the big O notation, like 6n plus 5, very specific. But it doesn't have to necessarily be that because there's not necessarily a distinction between a running time of 5n plus 5 and a running time of 100n. But they do let us distinguish between some running times and so determine some algorithms are faster than others. So if I wanted to compare those two algorithms, well, obviously the 5n plus 5, is a smaller number, and we like smaller when talking about big O. So that one would be better. But in the grand scheme of things, they're both an n to the power of 1. So because it's both to the power of 1, they're technically pretty close to being the same. And that's what we're going to see here when we start looking at graphical visualizations of big O. If we look at the graphs at right, and notice that all graphs of the functions are big O of n, they eventually fall below the graph of the function 0.5 n squared. And of course, 0.5 n squared is this crazy fast growing curve right here. All right, you can see that they all kind of roughly start off at the same point. Some of them go at different points than others, but these are all pretty much linear lines. You have t of n equals n, t of n equals n plus 2, t of n equals 2n. So if you write this in normal mathematical notation, for example, you might say, hey, y equals x plus 2, y equals 2n. All right, or f of x if you're more familiar with function notation. F of x equals x, f of x equals x plus 2, f of x equals 2x. All right, those are all linear functions. All right, whereas this one here is a quadratic function, 0.5 n squared. The result of what's going to happen over time as we start getting larger and larger problem size is that the big O algorithm is always going to be faster than any big O of n squared, provided we use large enough values. So once you hit this threshold here where this data set size can cross paths, so boom, 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 so right in here in this nice little window, this is when you definitely do not want to be having this kind of runtime. Because obviously down here, oh yeah, this looks great. But then you get to these larger problem sets, it's not quite as efficient. Now, although a big O of n squared algorithm could be faster than, let's say, a big O n algorithm for the problem size you're handling, programmers have generally found that in practice, big O of n algorithms perform better than big O algorithms for most practical applications that are intuitively large. All right, so that's a key thing to remember. Okay, these big O algorithms, that's all these guys right up here. They like those kind of things. Now, similar remarks can apply to two other big O running times. So let's take a look at those real quick. Now, before we look at all that stuff, just a quick bit of terminology to help us with our description of generic algorithm running times. So, for example, the term linear running time means a running time of t of n equals a of n plus b. So, like the ones that we looked at before, like 6n plus 5, that would be linear running time because it's a linear equation. A linear running time is always big O of n. So it's a linear function. It's n to the power of 1. A quadratic running time means a running time with a highest term of n squared. So if you had something like, 2n squared plus 5n, that would be a quadratic running time. Now, a quadratic running time, obviously, is always going to be big O of n squared running time. There are other ones, though, of course, besides just linear and quadratic. There are occasionally going to be ones that are more logarithmic in the running time formulas. Now, those are normally given without any base because change the base is just, again, a constant multiple. So if you see log of n, you can think log base 2 of n, but it would not be wrong to really think log base 10 of n. All right, so we just say, hey, it's log n. All right, we don't necessarily care if it's log base 2 or log base 10 because ultimately they're going to function very similarly in terms of their growth patterns, kind of like when we looked at the different linear functions. Logarithmic functions are very nice in terms of programming because they are very slow-growing programs. If you look at a linear curve, the way it graphs, it starts off really fast and then plateaus nice and easy. And so that's why logarithmic functions are actually pretty nice. So big O of log n running time, therefore, is generally pretty fast. Now, in many cases, our running time estimates may end up being better than the big O estimates. So when we specify a linear running time, that is a tight upper bound, and you can think of the running time as being exactly t of n equals c of n, although c is still not specified. So with all this being said, let's tie this back to our main topic that we were trying to talk about, which is that of the linked list. All right, so we know about Bayesian notation. We know how the running time can affect everything. So let's express the efficiency of various methods for our linked list data structures. So for an example here, let's analyze the runtime efficiency of an algorithm considering the find method for the class linked list 1. So this is all the way back from the beginning of the unit when we talked about a singly linked list. This method, therefore, is going to start at the head list and sequentially iterate through each node to see if it matches the target. If the linked list contains many nodes, well, then we might get lucky if the target is found at the head list. But if it's like 1,000 nodes, well, our luck is kind of going down here. So in this case, if it's at the head of the list, well, the computer only had to execute one step. Check the head for the list of target. Oh, okay, well, in the worst case, the computer might have to search through all n number of nodes to try and find or not find the target. Well, if that's the case, the computer had to execute n steps. And obviously, when we look at that, well, the worst case is going to take a lot longer than the best case. Base case, hey, look, you're right here at the head. Oh, we're done. We're going home now. But what if it's, let's say, it's at the tail? Then you might be there a little while. On the average, all right, we might expect to search through at least half of the list before finding the target. So we might get to, it may not necessarily be the halfway point. It might be like, if you have 100 links, it might be at 0.62. But on average, you're going to have to go through at least half the list. So this case would then require n over 2 steps. So our big O notation, we would say then, well, the find operation is big O of n. And why is it not like big O of n over 2? Well, because, remember, that divide by 2 is really the same thing as 1/2. And 1/2 would then just be a multiple constant. So it'd be 1/2 c, which would mean, if we're looking at the big O, we're just looking at big O of n. However, let's just say we look at our add to start method. Well, this requires linking a new node to the head of the list. Well, this runs in big O1 steps. That is a constant upper bound on the running time that is independent of the size of the input. And big O1 is beautiful. Boom. It's like just 1 all the time. So in our upcoming lessons, all right, we're going to explore a few other data structures that require a few steps. So right now we got big O of n. But let's see if we can find something that's even more efficient. So we can try and bring that running time down. Because while big O of n is better than, obviously, than big O of n squared, or any kind of other things like exponential would be really crazy. But there are ones that are more logarithmic in some of their scale. So we're going to look at those in some upcoming lessons. And with that being said, folks, I'm going to leave you right there.